Electronegativity is important because it dictates a lot of how bonding works. Again, one of our big questions about understanding geometry and reactivity are, where are the electrons? Particularly, where are the electrons in a bond? And so to go back from a bond to an atom, if we look at atomic orbitals, the energy of these atomic orbitals goes down, the potential energy goes down as we go left to right across the periodic table. So how should we think about that? Again, we just saw how fluorine really can hold electrons tightly to itself. And electrons are negatively charged. They like to be held tightly to a positive nucleus. That gives a low potential energy situation. And so again, if an electron on fluorine will be lower in energy, or more stable, as we'll say a lot, be more stable than an electron on oxygen, nitrogen, carbon, and so on. So why do we care about that? How do we use that information? Let's think about a carbon-fluorine single bond. So we've seen carbon-carbon bonds where those energies are about the same. What happens when one of those is quite a bit lower in potential energy than the other one? So the one thing that happens is that you have less overlap, and so the energy difference here can be pretty small compared to a typical carbon-carbon bond. So this is kind of not going that far down. But that doesn't mean it's a weak bond, right? If you think about it, to break this bond back in half, we would have to move this electron up a little bit in energy, but we'll have to move this electron way up in energy. So this is still a pretty strong bond, and that polarity gives it some of its strength. What does this sigma and sigma star orbitals look like? So the sigma orbital in the carbon-fluorine bond, I kind of think of like this, where there's kind of a big fluorine orbital and a much smaller carbon orbital. And they are mixing in phase here. But to some first approximation, we can think about this sigma orbital being very similar to just the fluorine orbital. The sigma star orbital, very close in energy to the carbon orbital, really much kind of just looks like the carbon orbital with just a little bit of fluorine mixed in. So when we build molecular orbitals from atomic orbitals, it's not always going to be a 50-50 share of electrons like it is in HH or CC. In fact, most of the time, it won't be. Most of the time, one of the atoms or groups will be more electronegative than the other. And so it'll be lower in potential energy, and the sigma orbital will resemble that orbital a lot more. And the sigma star orbital will put most of it on the less electronegative atom. What does this mean? It means that these electrons are, for the most part, on fluorine. And we knew that, right? When we draw carbon-fluorine bonds, we're used to thinking about those electrons being shared unequally. So this is kind of the fancy way to communicate this, that most of the electron charge is on fluorine and not carbon. Differences in electronegativity between bonded atoms actually make even more of a difference in pi bonds than they do in sigma bonds. So let's go back. Think about fluorine for a second. As I said, it's very electronegative, but it's also not very polarizable. It's kind of this little ball of solid charge, a thick candy shell of charge, as it were. But other atoms are more polarizable, particularly when we talk about p electrons, right? Now, and it's not like an s electron that's more concentrated at the nucleus. These p electrons are very diffuse and spread out. And so they're going to be more polarizable, able to be polarized. Big diffuse electron cloud, more responsive to external charges. So if it feels some positive charge, it's going to flow to that more efficiently than something that's tight and not polarizable. So an example, we're going to talk a lot about the carbon-oxygen double bond in this class, and especially in chemistry 252. So the orbitals look like this, right? We're going to build our pi orbitals from p orbitals, just like we did with carbon and carbon. again, my pi orbital is going to look a lot like this oxygen pi orbital. So these aren't great drawings. We can kind of think of them like this. Again, this is mostly the oxygen with a little bit of carbon mixed in. It's polarized toward oxygen. If I were to ask you, where are those electrons are on oxygen most of the time. This is not new. We're used to thinking about this as a polar bond. This is just a fancy way to communicate this. What does the pi star orbital look like? Well, it's mostly carbon with a little bit of oxygen built in, nodes and nodes. One last thing to point out. When we talked about sigma and pi bonds for carbon, I took pains to point out that a carbon-carbon double bond was not quite twice as strong as a carbon-carbon single bond. All right, so, and I justify that by saying, well, pi orbitals have weaker overlap. They're not that nice direct overlap that a sigma bond has. So sigma bonds are generally stronger, right? And so that's why the carbon-carbon double bond isn't just double a single bond. However, if I look at carbon-oxygen, the carbon-oxygen double bond is actually quite a bit more than twice the bond energy of the CO single bond. So that would seem to contradict what I said up here. Well, not really. Generally speaking, sigma bonds are still stronger than pi bonds. However, as we've shown here, this really big shift in polarity gives this CO bond a pretty big dipole. And that dipole, that negative and positive, helps hold those atoms together quite a bit more strongly than just the covalent bonding. So you can think of this as a mix between covalent bonding and ionic bonding. But I think it's that charge attraction that makes this carbon-oxygen bond so strong.